Okay, we're good to go. So yeah, hi, welcome. This is the recitation. So we're going to be going through steps of the solutions rigorously instead of chasing the answer. And specifically, this recitation, we're going to be doing chapter 9. Okay, so let's get started. So the first part is going to be a basic example that give us a situation, give us the data, and we're gonna essentially calculate the power of the test statistics, and we're gonna walk through steps of what that looks like. So let's go ahead and start writing the problem. I believe this is example 9.1.5. And the first thing we start with is the data. Just like MLE, just like when you find an estimator or asymptotic statistics, we start with data. So suppose x1, x2, all the way to xn. This is going to be a random sample from some sort of distribution. Let's say normal. From normal, mu sigma square. And let's say we want to test hypothesis. So this is going to be our goal. Let me zoom in a little bit. So goal here, we have a null hypothesis. Let's say mu is mu naught versus alternative hypothesis, H1, that is basically not equal to mu naught. So that's the standard setup of a hypothesis testing. The idea is following. So this group of data that we're having right now, you kind of know that it's from normal mu sigma square, but this mu, we actually not sure what that is. So to be specific, here we're gonna say mu unknown, and that's what we want to know. And specifically, we have this like target of interest, right? Like mu naught is something we're interested in find out. So usually the idea is the following. So I'll say idea. First is you find out the xn bar specifically, and this is going to be your sample mean. And in connection with this, sorry about that, I think I'm getting cut off. Can you guys still hear me?
Yeah, you're good.
Okay. I'm sorry. I thought I'm getting cut off. Okay. So in regarding to this xn bar, really what we need is asymptotically, we want to get an idea of what this thing look like, and then we want to compare that with mu naught. And we're gonna give you an example of what that looks like. So one is to find out the information of xn bar. Two is compare with mu naught. Okay, so when we compare this xn bar to mu naught, really we're talking about a set that we can refer to, and if it's in a set, maybe we have one set of conclusion. Outside of the set, we have another, and specifically that essentially referring to do you fail to reject your null hypothesis or do you reject your null hypothesis? So the decision making is like this. So decision making. Essentially, we're looking at a set. I'll just call it S0 to indicate the set that is for the null hypothesis. And this is going to be referred to the type of X such that, so the column means such that this xn bar minus mu naught is within a certain range. Now, as of this point, we don't really know what that range is. So we're just going to use a random number, like random letter. We're going to call it C, something like this. So it's within this range C. So the set, if the difference of xn bar and mu naught is within the set. So if this, so this is our data, by the way, this is our data. So this X is our data. Let's put that in. And technically speaking, this is your set. So the group of data that we have, this X, such that makes this XM bar minus mu 0 within this range minus C and plus C, then we fail to reject null hypothesis. So then fail to reject. So that's kind of like the decision-making process here. So now the question is very straightforward. So now the question is, okay, since the set is what we need, then we should investigate the set. So then the idea is you say, okay, so let's take a look at this set and what can we do about it? Okay, so if you look carefully, it should be like, you can kind of think of like a straight line like that. And then what is happening is you have a, I'll just make some random bar, like, let's say that's C. So that's C there, and then maybe that's minus C. And then you can kind of get an idea of the data kind of falling like this in the middle if you are fail to reject. So we're going to use a green color, something like this. So this is going to be fail reject. And then outside of this green area, you also have the red area, just like that. So if you're outside of this red area, then you reject null hypothesis. So here you reject. And this is null, by the way, so say reject null. So that's kind of the idea. So so now since well, technically speaking, most of our data can only help us get XM bar. So that's kind of the idea. So we need to do a little bit more work. So what I mean by that is we need to make sure that this XM bar in the middle of this equation, there's this mu naught here. So we want to move this to the left and right hand side, just like that. And to do that, we need to plus mu naught on both sides of the equation. So what I mean by that is we plus mu naught. So left hand side will be like that, and right hand side it will be mu naught plus C. So then that translates the previous formula into a formula that's just about XM bar, nothing else. And then you can ask the question, okay, what is the power? What is the power of test? Something like this. And the power of test is another way of asking, okay, what is the probability under the curve? And the probability is under the curve. This curve is essentially referring to the rejection region. So in other words, the answer is really just asking probability of test statistics in rejection region. So that's really the idea here. And we can write that out. That is exactly equal to, well, the red area. So this and this. And that's the, so you give me this line, and then there's C and C minus C. There's a green area, there's a red area. And the red area, the probability that it falls on the right area is going to be exactly the value that we want here. So with that being said, we can write it out. There are, of course, a couple of things to do this. I'm going to use the most basic way. So what I'm going to do is I'm going to leverage exactly what we derived here. But notice that if you are within this region, technically speaking, you're on a green area. So the red area is a complement of that, right? So in other words, we need to write 1 minus probability mu naught minus C less than equal to XM bar less than equal to mu naught plus C. So that's a setup. We want the red area, so we take 1, subtract the green area. And now the rest is a little bit of algebra. So first thing you notice is, okay, we have essentially a range. So what that means is we can essentially rewrite this into like just use a mathematical notation differently. So it'd be like probability x n bar greater than equal to mu naught plus c, or x n bar less than equal to mu naught minus c. So in other words, I'm saying this equation, it's conceptually the same as the value of this probability, which is the set that you fall out of this C and fall less than this minus C, and those regions together is going to be the rejection region. So now this or is just English, so it's not really rigorous. So I'm going to write it out a little bit rigorously by using actual math notations. So that is going to give us x n bar greater than equal to mu naught plus c plus probability x n bar less than equal to mu naught minus c. All right, and now here is the trick. The trick is essentially use CLT. So what I mean by that is in the previous chapter, and this is a little bit review. Let's say I give you so here I'm gonna write a small draft. I say recall. So this is kind of like a sketch. Okay, it's not like part of the equation. It's like a sketch. So recall previously we have our data, right? X1, X2, da 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 da, Xn, and then what do we have? We have sample mean, right? So let's say sample mean is Xn bar, and oh, by the way, this has come from say with mean mu and variance say sigma square, something like that. And in that case, and let's assume that both the mean and variance are known to us, and we can compute sample mean to be Xn bar. So now what's interesting about the sample mean is you know that the sample mean has expectation to be exactly mu, and then the variance of the sample mean to be sigma square over n. So then the idea is by central limit theorem, you have what? Xn bar minus mu over, don't forget the square root, and something like this. That's going to be your standard normal. So 0, 1. And that's the trick that, sorry, not trick, that's the theorem that we're going to use in solving this problem, which essentially you can kind of think of like this. In hypothesis testing, we want to understand what's going to happen, like at its limit, right? It's limiting behavior, what is going to happen. And we borrow what we know from CLT, central limit theorem. So with this in our head, now all we got do is we want to somehow turn this thing look like that. Because if you just give me this, I can't actually just directly use CLT. It can't actually, I'm not allowed to do that. So the work here is to do a little bit of translation. So this Xn bar, what do we have? This Xn bar, I can make it look exactly like this. And that's what I want to do. So I'm going to do subtract mu. Now, if I do that, the right-hand side, I also need to subtract mu, right? So that's step one. And then I also have the bottom part. I can't forget that, right? So I need to essentially divide it by this asymptotic variance. On top of that is a square root. So asymptotic standard deviation, which is this sigma square over n thing. So let's do that. Over square root sigma square over n. And since I did that to the left-hand side of the equation, right-hand side, I have to do the same to ensure that the equation doesn't change, to ensure the sign of the equation doesn't change, parentheses. So that's what I need to do for for the first term. All right. Now, before I write a second term, notice that the first term is greater than equal. So that's not really mathematically, that's going to give me a little bit of issue. And the reason that is because when we write, this is just notation. So I'm going to denote, let's say I denote standard normal to have distribution function phi, right? Phi something in here. So exactly what that means is a probability that z is less than some value z. This is the CDF of normal 0, 1. All right. So now notice that when I write something like this, the convention of the notation is here, less than equal. Okay. So that is why if I want to use anything here, any of my previous knowledge to make my math easier, I need to change the sign. Okay. And how do I do that? I can simply just, you know, do a 1 minus in front of it. And the reason is because, well, less than equal is a complement of greater than equal, because they're, you know, within the same set, add up together to be 100%. So if it's not less than, it better be greater than. So they're complement of each other. And the rest, and now we'll finish the first term. The second term, it's essentially just a direct replication of the first term. So we do xn bar minus mu, and then we do over square root of this sigma square over n, and then this is less than equal, and same thing here, but this is minus c instead of plus c. Don't forget the minus mu, and this is over square root. And what we have here is the asymptotic variance of the x bar n, and then we square root of it. And that will give us the standardized term of this xn bar on the left-hand side. So now, since this is what? This is really just a normal 0, 1, right? Because we derive here, normal 0, 1. So we're allowed to essentially use phi to rewrite this formula. So I am making a small mistake here. That is going to be minus less than or equal. So now we're great. Now we're good to go. Now we have left is essentially replace this with phi. Now notice that here, since I have this to be probability, this can be less than or equal to z. Now I'm going to write a z here, something like this. So whatever's inside this parenthesis is going to be the input of, essentially you can kind of think of it as like the exact cutoff, such that when z is less than this small z, it's like some percentage, because that's a CDF. It's, you know, it's a cumulative distribution function. So here the notation is I can directly just plug this in here. So I'm going to write that. And don't forget the standard deviation over standard deviation, just like that. And that will be your final answer for this problem. So let me pause. Any questions about this part? Good.
So just to recap what we did here. What we did is we compared our sample mean with mu naught, and we found a set of events where the distance between xn and mu naught falls between some number c. And then we found the probability of that event happening.
Yeah, that's correct. Yes.
Perfect. At any point, did we use a power function?
I'm essentially just calculating here. That's the power of the test statistic in the rejection region.
So is the power function different from the power of the test, or are they the same?
Well, here, I'm referring to the probability of you falling in the rejection region, which is essentially this area plus this area.
Yeah, I follow that.
Yeah, sorry, is that your question?
Oh, no, it just the textbook mentions a power function. And I was wondering if this was the kind of context where that would come up.
Sorry, come up as what in the exam or?
No, as in if that's something that would be utilized in this example.
Yeah. So I'm essentially referring to, so when I say power of the test, I'm essentially referring to this formula here. Yeah.
Mhm.
Yeah. So I think there are a couple of students joining late. So just a small recap. What we just did was essentially walking through example 9.1.5. And the idea here is we're doing a hypothesis testing. And instead of chasing answer, which I'm sure you guys all know the answer, what we want to emphasize here is essentially investigate this set. And this set is essentially this line here that you have like a green area. That's when you fail to reject the null hypothesis, versus this red area. That's going to be the area when you do reject the null hypothesis. And the power of the test is essentially, the power that events happens, that events occurs when you reject the null hypothesis, which we essentially carried out the calculation somewhere on the bottom of the paper. Most of this is I wouldn't say tricky. I would say most of this straightforward. The only thing I can think of it might be tricky is the usage of this. It actually depends on the so what I think can trick people is this part. It really requires you to understand the asymptotic normal and the asymptotic behavior or limiting behavior. Anything comes to those keywords is essentially referring to, okay, I have this xm bar. What do I know about this thing when it's at its, say, limit? That's kind of the theorem or the trick that we need to use here. This is an easy example because we want to make sure everyone understands it. So we use xm bar, but in reality, it can be literally anything else. And you may or may not know the asymptotic distribution for this xm bar or for whatever it come up. Next time, if it's something else, then you need to either you memorize it or you need to rederive these two things, which can probably be a little bit time costly if it's during the exam. So I just want to make sure that you guys know that where this thing come from. It's coming from this guy here, and usually if it's discussed in class, you can directly use it. You can say, hey, this is a theorem, whatever, like 7 point something, 8 point something, 9 point something, and you just use it. In some case, I've seen that either students don't remember or somehow it's not on cheat sheet, then you can derive it on the spot in the exam. It just takes a little bit more time, but it's not it really just adds maybe like a few more lines of your solution, and that's it. Does that kind of make sense? So I'm referring to essentially the trick on this line here. It's coming from left hand side. Okay, so let's move on from here. The next problem, this is recorded, by the way, so it's usually it's on YouTube. If you miss anything, don't worry about it. You can always go on YouTube, and if you miss anything, if you still don't understand anything, you can always email me. So yeah, so don't worry about that much. Let's continue from here. The next example we're gonna do is example 9.2.6, and this is an example that's about Bernoulli. So let's write that down. Bernoulli. And we have the same setup, right? We suppose we have all the data, x1, x2, xn, and well, it's from a random sample from Bernoulli. So let's write that down. Random sample. This is from Bernoulli. And Bernoulli has a parameter p, right? So we're gonna make sure that we write that down, p. And then more specifically, p is unknown. And then you can kind of guess, well, since this thing is unknown, then obviously the goal is to test it, right? So in this case, we have a rather special hypothesis test for p. The null is p is 0.2 versus the alternative is p is 0.4. So this is kind of like a, I wouldn't say special, but it's kind of look a little bit weird, right? It's not like one side or two sides where we're seeing before. It's like two particular number. So that could, strike some people off a little bit. If you haven't seen this before, it could look a little weird. But that's okay. We're gonna, walk through what's going on here. So the first thing is we need to essentially recall what we know about Bernoulli. So if I tell you this, this is a recall. If I say just very simple, x, just one observation, x, is from Bernoulli. Let's say p. So then exactly what that means is f of x equal to p if x is 1, and f of x equal to 1 minus p if x is 0. Or some people write like this. This is 1, I'm sorry, this is p, this is 1 minus p. This is if x is 1, this is if x is 0. They're essentially talking about the same thing. So because this is our definition, so it's kind of like in the nature that in the definition that this x can only take value 0 or 1. So that's the essentially you can call it support. I call it support just the notation from real analysis, but if you haven't taken that, you can kind of think of it as essentially just the values that x are allowed to take, and that's it. Because if it's outside of this range, then f of x is not defined. So that's important. I think earlier some other students asked me about indicator function. That's also where the indicator function is coming from, which essentially it's a mathematically faster notation of saying, okay, if something's within this range, then we give it a 1, otherwise 0. So we replace with 0 if it's outside the support. Otherwise, it's originally as it is. Okay, so that's Bernoulli. Hopefully that's clear. So when it comes to Bernoulli, and we have n samples, right? Here we have 1, 2, all the way to n. So the joint PDF or PMF, here it's a PMF. So the joint, I'll just write PMF. Is let's notate this by Fn, and this is essentially the product of our n terms, and exactly what we're talking about is something like this. Now, since let me just write it out first. So this is going to be the product I from 1 to n, and let's write out pxi 1 minus p 1 minus xi. Okay, and don't forget that xi is in 0, 1. So now, with that being said, we can talk a little bit. So here, what's interesting is the following. Since xi can only take 1 or 0, so you're better off just directly write out the joint of the likelihood function, and then you want to replace the summation with like another letter. So what I mean by that is the following. So here, if I equals to 1, right? If this is 1, then this is 1, this is 1. So let's write that out. What is this? This is x1, 1 minus p, 1 minus x1, and then x2, right? Because this I can be 2. So 2 here, 2 here. Then what that means is you get something like this, 1 minus x2. So then you get the idea, 3, 4, 5, all the way to n. Then notice that here you have x1, here you have x2, and then here you have like a px3, right? So these guys, you can kind of put them together. So you can do something like this, summation xi. And then don't forget that you have the second term, and the top is kind of look the same, 1 minus x1, 1 minus x2, and here have 1 minus x3. So we can put all them together. So that all that together is 1 minus p. This is n minus summation xi. All right. So now we're going to make our math a little bit easier. So denote y to be summation of xi, just to make our math slightly easier. So after the notation, we have essentially this thing, p to the power of y, 1 minus p to the power of n minus y. So now, this is everything that we've done before, right? In previous chapters, we have PMF, we know the support, we know what's going on, we know the likelihood function, like all that's is consistent with what we've done before. So now we can think a little bit like this. This is actually just one value. It's not like greater than 0.2, right? So it's just one value. This is also just one value. And in the entire real numbers, we're just talking about two numbers here. So if you're looking at the entire real set, the null and the alternative is not going to add up to like 100%. Okay, so because of that, you essentially cannot use what we have before, right? So that's important. Right? You can't use what we have before. So here it's the reason why you need to use a likelihood ratio test instead of using the conventional hypothesis test, like z-test, something like that. So how do we do that? Well, we have this thing here, right? Hopefully in the exam, you're not going to see anything too weird. I'm hoping that all students have seen essentially all distributions as an exam before. Now, if that's not the case, then you can do this kind of derivation on the spot in the exam. But hopefully you can just directly, if you know this, you can directly write that. I'm writing this simply because I want to make sure that everyone follows. But if you know what this is, you can directly write this, no problem. Okay. So that's just to let you guys know a little bit of a time-saving technique. All right, so let's continue. So what's happening here? Under null. So under null, what happens? P equals to 0.2. That's the assumption, right? That's a hypothesis. Under null, P is 0.2, 20%. Okay, so let's plug that in. I'm using this notation 0 here to indicate that that's the situation of f and x under null, and null is 0. So here we say we plug in p equals to 0.2. So what that means is we have 0.2 to the power of y, 1 minus 0.2 to the power of n minus y. And obviously this is 0.2 y, 0.8 n minus y. All right. So that's for null. How about under alternative? Under alternative, what is p? P is 0.4, 40%. 40%. So I'm going to use this notation f1. This f1 does not mean one observation. It means the f and x under alternative hypothesis. Okay. And so we plug in 0.4, 40%. So 0.4 y, 1 minus 0.4 n minus y. And do a little bit of math. That is 0.4 y, 0.6 n minus y. All right. So yeah. Okay. So here we essentially worked out the joint PMF or joint whatever PDF under null versus under alternative hypothesis. And these values are essentially taken from the problem. All right. The likelihood ratio test, well, it's a ratio, right? So we're talking about something over something. So let's write that out. Likelihood ratio. The conventional way is to write the alternative on top. Okay, so something like this. And we should have all the pieces that we need. So the rest is just math. So let's plug this thing in. Let's plug in f. So that's not a. It's a 0.4 y. That's for f1x. 0.6 n minus y over. That's the f0x. So that's 0.2 y, 0.8 n minus y. And the way I avoid mathematical error is I split them up. So that's going to give me 4/2. That's y. And then this is going to be 0.6. So I'll just do 6/8. That's going to give me an n and another 6/8 minus y. And then this minus y, I can flip it. So that's going to be 8/6 y. And then you notice that the second term and the first term can be essentially multiplied together. So first term we have essentially 2/1. And let me just double check. And then the second term is, so 8 divided by 2, that's 4, and that's 3. All right. And let's see, sorry, let me make sure I'm not making any error. So what do we have here is, all right, so I'm gonna combine this, and that's gonna be 8/3. Let me know if I make any error. That could happen. And then what we have here is, what we have left is 3/4. That is for n. So this is going to be essentially a final result for the likelihood ratio. So whatever this is, like we call this, let's just call it triangle. All right, so that's a result. It's kind of like it's a specific numerical result. Okay, so once we have this, it's a result of a ratio, and it's a ratio of two things, right? One is alternative, one is null. You can kind of intuitively think, if this ratio is large, then what's happening is the probability from top, from the null, from the alternative hypothesis is much greater than null. So then in that case, you can kind of guess that, okay, then maybe this guy is true. The reverse is the same. If the value is too small, if this is a small number, then what that means is either this is small or this is large. Either way, you can kind of conclude that the probability is probably 20%. So that's the idea here. So now here, you can say that essentially you say reject. So the conclusion is reject null if this triangle is greater than some sort of value k. And this k is usually somehow provided in the problem. The problem will tell you what k is. Here is just a generalized solution to show you that the key here is to work out the likelihood ratio a function, and that results we're going to compare with k. I think there's a standard rules that there's 1 and then there's 2, and this triangle is greater than 1 or triangle is greater than 2, and you can kind of conclude that you reject the null, something like that. Me personally, my intuition is always stick to the problem. You only go there if the problem doesn't tell you what that is. Does that kind of make sense? So that's kind of what's happening with this example. So let's take a quick pause. Any questions about what I just said, what we just done in this example?
No, it's pretty clear.
Cool. Thank you. Thank you. Awesome. Let's continue. I think we just have one more problem, and we should be able to finish before time. Yeah, so hopefully you guys can have some time for questions, or you can go home and study for the exam. All right, so next question is example 9.5.4. What are we doing here? Okay, so here we are talking about I believe we're talking about a z-test. Let me just double check. Yes. Okay, so this is the length. The title of not title, sorry. The example is about length of fibers. So that's kind of like a situation. This is situational. So length of whatever metal fibers. Yeah, so usually it's like or drug defect, right? Like anything like that, like a real world situation. But it doesn't matter. The setup is the same. So you collect data. X1, X2, da da da. Now, in real world, you're not gonna get an n that's infinitely large, right? I'm not gonna do this n and n goes to infinity. That's not gonna happen because it's in real world. There's always gonna be some sort of upper bound. 1,000, 10,000, a billion, right? There's always upper bound. You're not gonna get infinite. So here in this example, they give you 15. And also they kind of guess that, okay, so this is a essentially random sample from normal. Mu, they don't tell you what that is, sigma square, and they don't tell you what that is. So none of these two parameters you know. So both of them are unknown. You don't know what that is. Now the goal is hypothesis testing. So now hypothesis, what is that? That is mu less than equal to some arbitrary number 5.2 versus H1, that's alternative. It's a complement of null, so mu is greater than 5.2. Since this is an example that you do not know mu, you do not know sigma square, so you want to do a z-test. I'm sorry, you want to do a t-test. So if you know them, you can do a z-test. But now, since you don't know them, you don't have infinite sample, then it's a t-test. Make sense? So let's write that down. Since here, mu sigma square unknown, we do a t-test. I will write that down. All right, so that's important. Okay, so it's not like things are completely different. We're still following the same procedure. The first thing is obviously sample mean. In this case, you're not going to get an xm bar because we don't have infinite, right? We have 15. So it's going to be x 15 bar, x 15 bar. This is going to be your sample mean. So the sample mean is essentially everything adds up together divided by 15. So 1 over 15, x1 plus x2 plus da 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 plus x15. Either the problem tells you, or the problem is just going to give you 15 numbers and you just work out the math yourself. So here, I think the problem tells us, so that's 5.4. Let's write that down. And same with sigma. This sigma is a sample standard deviation. Sigma, this is going to be 0.4226, right? So I think the problem also tells you this as well. And I don't think they will have a problem that asks you to compute this from scratch. It's kind of tedious to do that. Let's take a quick look at what's going on here and where does the t come from. So let's do a recall. So recall, if you have like finite sample, like not infinite, like finite. So suppose x1, x2, to xn, and also assume you can compute sample mean and sample standard deviation. So the formula is mean, fortunately, that stays the same. So everything adds up together divided by n. The sample standard deviation, unfortunately, is a little bit different. So let me write out the sample variance first. That is going to be, unfortunately, there is a n-1 here. And then there's a summation I from 1 to n. Obviously, you have xi minus xn bar. And xn it's estimated from here. So this xn is estimated from here. It's not from a problem, or because you don't know that, right? So it's estimated from sample mean, and same with sample variance. All right, and here the test statistic. If you want to do hypothesis testing, so you can kind of think like this: test statistic is what is essentially xn bar minus mu. Let me be clear. This is if I want to test. Xn bar equals to mu versus x naught. Sorry, alternative is xn bar not equal to mu, something like that. Let's say that's my test, and this is like some arbitrary number, right? So what's going to happen is I need to divide this by standard deviation of essentially this thing, where this is from above. Okay, so mathematically, you can kind of see that this is not a conventional z-test that we see. And the reason is because this is estimated, and there's only n-1 in the bottom. And because of that, this is actually gonna, so if I call this u, so let's call this u. Wow, that's terrible. Okay, let me rewrite this. So we call this u, then this u actually come from t distribution with n-1 degrees of freedom. So this is t distribution with degrees of freedom to be n-1. All right. So that's how it's supposed to happen, right? Under null, that's how it's supposed to happen. So you compare with that. If the results is completely out of the way, too far from the critical value, which actually comes from t distribution, then you reject null hypothesis. So that's kind of the idea here. So in this example, fortunately, the numbers they all told us we don't have to do any of this stuff because they told us here. We can literally just plug in a number. So here it's 5.2. So we have all the pieces that we know. So in this example, the test statistics U is what? This is 5.4, this is 5.2. So let's write that down. 5.4 minus 5.2 over, we have this guy here. So this is, what is it? 0.4226. So 0.4226 over square root of 15. All right. This is a standard deviation, right? Yeah, so I don't have to take a square root because it's already in the standard deviation form. And you work out the math. This is going to be about 1.83. And then you compare with the critical value. So the critical value is going to be essentially the t distribution This is degree of freedom, so that's n-1, which is 15 minus 1, so 14. And then the problem should tell you what is the alpha. So this is 1 minus alpha, and then that's inverse. This will give you the critical value. So let's say n is 15, and then alpha, it's at alpha, say 5% significance. Then your critical value is T14. Don't forget the inverse. 1 minus 5%, so 100% minus 5%. So that's 95%, right? So 0.95. This is going to give you about, let me check my table, 1.76. Okay. So now this is rather easy to compare. 1.8 is bigger than 1.76, so we reject the null hypothesis. So let's say here, thus reject null. So reject null, you can, I'm not gonna write here, but you can add one more sentence down here. Reject null just means that the conclusion is the population that these data is coming from probably have a mu that is greater than 5.2. So whatever metal fibers that we're looking at in the data, because the data only give us 15 numbers, right? It's not like this is not like the entire population. It's just 15 samples. So we work out our math, we do all of this work, and we come up with this conclusion. And what that basically means is, okay, based on these 15 samples, and based on the test results, what we're going to conclude here is the population that this 15 samples come from has a mean greater than 5.2, which is essentially what this statement's H1 is saying, the alternative hypothesis, which essentially is what that's saying. So if you want to, you can maybe write a little bit. Sometimes I've seen questions leave like usually there's like a B, C, and then sometimes people ask a part D. They ask like, how do you interpret the results? And my guess is that probably won't happen. But if that happens, that's going to be the answer. So exactly what I said. Just conclude that and notice that this mu is not the mu from 15 samples, because 15 samples mu is here. Like you don't need to conclude that, it's done. You're concluding this thing, which is from a global population. All right, so let's pause here. Any questions about this example? The key here is a t-test. Good?
Yeah.
Good, bad, questions?
Yeah, so just to recap, I think the common thread here is we're trying to find the set or the event space that corresponds to our null hypothesis. And then we're going to try and transform it either based on the central limit theorem or the likelihood ratio test or by the t-test. And then find the probability of that event space after that transformation.
Yeah, that's correct. Yeah. Cool, awesome. Today was well planned, so it's exactly at 10 o'clock. So that's pretty good. I can, of course, stay over a little bit in case you have questions. But if not, you're feel free to drop off. And I think I will, I think I'm gonna proctor a session. So hopefully I'll see you in my session. If not, it's totally okay. Good luck to all of you for your midterm.
Thank you, Michelle. Have a good one. Bye.
Yeah, you got it. Take care.